Alrighty, let's have a quick look at writing the electron arrangement, also known as the electron configuration. We'll start with boron. The atomic number of boron is 5. Remember, capital Z says atomic number. It's German, the word Zahl, meaning number. So Z is atomic number 5. What that means is that boron has 5 protons, but we know that the number of electrons is the same as the number of protons. So we have 5 electrons to place into shells. We put 2 electrons into the first shell. That shell is now full, so we have to move to the second shell. We've only got 3 left, so they will easily fit in there. So the electron arrangement for boron is 2, 3. Moving on to another example, this time fluorine. Fluorine is number 9 on the periodic table because it has an atomic number of 9. So we're going to have 9 electrons to place into shells. 2 into the first shell, 7 into the second. Our electron arrangement for fluorine is 2, 7. Now when we're doing this, we need to keep in mind 2n squared. This is, of course, telling us how many electrons could possibly fit into a shell. It doesn't tell us how many there actually are, but how many could fit in there. You can think of n as the shell number. So in the first shell, n equals 1. 1 squared is 1 times 2 is 2. You can only fit 2 electrons into the first shell. The second shell can take 8 because n equals 2. So 2 squared is 4, and then times 2 is 8. Now, how many electrons can fit into the third shell? N equals 3. So 3 squared, that's 9. Then we multiply by 2, we get 18. So the third shell can take 18. It can fit 18 electrons. So do keep that 2n squared in mind. Like I say, n is the shell number. Well, at the moment we can think of n as the shell number. When you do more senior chemistry, you'll know that n is the principal quantum number, the first of the 4 quantum numbers. But anyway, for now, shell number. Now let's get out of that second shell. Let's go past that. We'll go with aluminium, atomic number 13. We're going to have 13 electrons. So 2 in the first shell, that is full. We move on. 8 into the second shell, that is full. We move on. We've still got 3 electrons. The third shell will quite easily take those 3 electrons. Our electron arrangement is 2, 8, 3. Now, as we approach the 19th and 20th elements, that would be potassium and calcium, we need to keep in mind that the 19th and 20th electrons actually go into the 4th shell. So let's take a look at potassium. The atomic number is 19. We have 19 electrons. Okay, so 2 in the first shell, that's full, move on. 8 into the second shell, that's full, move on. We've got 9 left. Now, that third shell can take up to 18. What we don't do is put the remaining 9 electrons into the third shell for 2, 8, 9. Remember, the 19th electron goes into the 4th shell. So we actually have an electron arrangement now of 2, 8, 8, 1. We know that that third shell isn't full. It can take up to 18, but that 19th electron goes into the 4th shell. If we were looking at calcium, the next electron would also go into the 4th shell. So calcium's arrangement would be 2, 8, 8, 2. Note that only those 19th and 20th electrons go into the 4th shell. We haven't moved on from the 3rd shell and now we're filling up the 4th. So if we were to choose an element larger than calcium, let's say iron, atomic number 26, we have 26 electrons. 2 into the first shell, that's full, move on. 8 into the second shell, that's full, move on. We put 8 into the third shell, and then the 19th and 20th we put into the 4th shell. So that covers the first 20 electrons, but then we have another 6. Well, remember that third shell wasn't full, so we actually come back to it and put our remaining 6 electrons into the third shell. So the electron arrangement for iron is actually 2, 8, 14, 2. So that third shell will be filled up for the 10 elements after calcium. The next 10 elements, we come back and fill up that third shell up to the 18 that it can actually take. Now, some people might have the question, well, why the heck do we do that, other than because you just said we have to? Well, if we consider what shells actually are, they correspond to a certain amount of energy. So if we plot this energy up the side versus shell number along the bottom, we can see that the first shell has a certain amount of energy. The second shell, if you want to be an electron in the second shell, you're going to need more energy. The third shell occupies even more energy, and the fourth shell even more energy. But what we can note is that there's actually a bit of overlap between the third and the fourth shell. So this explains why the 19th and 20th electrons go into the fourth shell. It's due to that overlap that we have in terms of energy levels. If you go on to senior chemistry, you'll write the electron arrangement more like this. So here's the electron arrangement for iron. Instead of the 2, 8, 14, 2, we actually now have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. This is how electron arrangement is actually written. When you do year 11 chemistry, this is what you'll be writing. This version of electron arrangement actually gives us more information because within a shell we actually have subshells S, P, D, F, and within a subshell we have a number of electron orbitals which can either take 1 or 2 electrons. It gets a little bit more complex, but we have a nice little Aufbau roadmap to follow. And if we follow this, we can see that we actually start the 4s, so that's part of the fourth shell, and it can take 2 electrons before we come back and go back to the 3D. So we're now back into part of the third shell. A D subshell can take 10 electrons. So that accounts for those extra 10 electrons when we move past calcium. Remember, we come back and put the next 10 electrons back into that third shell. We're filling up the 3D orbitals. But that's the senior version of electron arrangement. And this video is about the junior version. So we are done. Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.